Light, a fundamental aspect of our universe, is more than meets the eye. It is a complex interplay of waves and particles that give rise to a myriad of phenomena fundamental to both nature and technology. To understand how light behaves, we delve into three primary interactions: reflection, refraction, and diffraction. These phenomena reveal the many faces of light and its interactions with matter, enabling us to harness its potential in myriad ways. Reflection is perhaps the most familiar behavior of light, seen every day in mirrors and shiny surfaces. At its core, reflection is the change in direction of a wavefront at a surface, causing the wave to return to its origin. This phenomenon occurs when light rays encounter a surface that is smooth on the scale of the light's wavelength, such as glass or polished metal, where specular reflection dominates. Specular reflection follows the law of reflection, which states that the angle of incidence is equal to the angle of reflection, both measured from the normal to the surface. In contrast, when light hits a rough surface, it scatters in multiple directions due to diffuse reflection. This is why objects appear the same color from every angle. The surface irregularities cause light to reflect at many angles rather than a single, predictable one. Understanding reflection is crucial for designing optical devices like telescopes and cameras, where precise control of light paths is necessary. Reflective surfaces have been utilized since antiquity, with early mirrors crafted from polished stone and metal. Modern advancements have led to the development of mirrors coated with thin layers of aluminum or silver, enhancing their reflective capabilities. Additionally, the study of reflection has furthered our understanding of optical illusions and the development of technologies like periscopes and various types of sensors. Refraction is another fundamental characteristic of light's interaction with matter, occurring when light passes from one transparent medium into another, changing its speed and, consequently, its direction. This bending of light is governed by Snell's law, which relates the angles of incidence and refraction to the indices of refraction of the two media. The index of refraction is a measure of how much light slows down in a medium compared to in a vacuum. A classic example of refraction is the apparent bending of a straw placed in a glass of water. As light travels from air into water, its speed decreases, bending the light rays and making the straw appear to be broken or shifted. This bending is also responsible for natural phenomena like the shimmering effect of heat waves on roads, known as a mirage, where light refracts through layers of air at different temperatures. Refraction has numerous applications in optics and engineering. Lenses, the core components of glasses, microscopes, and cameras, utilize the principles of refraction to focus light. Lenses are crafted with precise curvatures to bend light in specific ways, aiding vision correction and magnification. Refraction is also critical in the design of optical fibers, which use repeated internal refraction to transmit light over long distances, enabling high-speed internet and telecommunications. Diffraction involves the bending of light waves around obstacles and the spreading out of light waves when they pass through small openings, a behavior that highlights the wave nature of light. Unlike reflection and refraction, which are concerned with light behaving in a straight line path, diffraction illustrates how light can spread and interfere, leading to the creation of characteristic patterns of light and dark regions. The extent of diffraction depends on the relationship between the wavelength of light and the size of the obstacle or aperture. When the aperture size is comparable to the wavelength, diffraction effects are most pronounced. This is why diffraction patterns are more evident with sound and radio waves, which have longer wavelengths than visible light. One of the most significant applications of diffraction is in the area of diffraction grating, a tool used to disperse light into its component colors or wavelengths. It is widely employed in spectroscopy to analyze the composition of light sources, including stars, helping astronomers understand the universe. Diffraction also plays a role in the minute details of CD and DVD functionality, as these devices rely on laser beams reading tiny tracks on their surfaces that act like diffraction grating. To delve deeper into the physics of light, we must explore its dual nature. The wave-particle duality of light is one of the central tenets of modern physics, describing how light exhibits properties of both waves and particles. This duality was first proposed in the early 20th century when experiments such as the double-slit experiment demonstrated interference patterns typically associated with waves, while the photoelectric effect revealed particle-like behavior. On a wave level, light or electromagnetic radiation encompasses a spectrum, ranging from radio waves with long wavelengths to gamma rays with very short wavelengths. Visible light is a narrow band within this spectrum, detected by the human eye. Wavelengths determine the color of light, with shorter wavelengths appearing blue and violet, while longer ones appear red. Light's particle-like properties are described through photons, discrete packets of energy that carry electromagnetic force. The energy of a photon is directly proportional to its frequency, as defined by Planck's constant. This relationship informs our understanding of phenomena such as the photoelectric effect, whereby photons strike a material, releasing electrons and creating an electric current. This effect is exploited in solar panels to convert sunlight into electricity. Understanding reflection, refraction, and diffraction allows us to appreciate and harness a broad range of optical phenomena. Rainbows, for instance, are a stunning natural display of refraction and internal reflection within water droplets, where different wavelengths are separated to form a spectrum of colors. The blue sky and red sunsets we admire are attributed to the scattering of shorter wavelength blue light and the longer paths red light takes through the atmosphere, an effect known as Rayleigh scattering. In technology, mastery over light manipulation has led to innovations such as lasers, which rely on the organized emission of photons to produce coherent beams of light. Lasers have transformed medicine, industry, and communications, from precise surgical procedures to high-power cutting tools, and the backbone of fiber optic networks. Similarly, optical fibers, utilizing total internal reflection, allow light to travel long distances with minimal loss, a feat vital to modern communications. By continuously refracting light within a glass or plastic core, vast amounts of data can be transmitted rapidly and efficiently across the globe. As we stand on the brink of new technological breakthroughs, the physics of light continues to illuminate possibilities. Advances in photonics, the science of generating and harnessing photons, promise innovations in areas such as quantum computing, where light's properties offer new ways to process information rapidly and securely. Photonic devices are poised to redefine computing power and data transmission, bringing even more remarkable efficiency and security to the digital age. In conclusion, the physics of light, encompassing reflection, refraction, and diffraction, is a field rich with both fundamental and applied insights. From the behavior of light in natural phenomena to modern technological applications, understanding these interactions not only increases our grasp of the universe but also fuels innovation across disciplines. As we continue to explore light's intricacies, we push the boundaries of what is possible, ensuring that its magic and mystery remain a source of inspiration and progress.